On May 16th of 2025, a major tornado outbreak took place across the southern Midwest, affecting Kentucky, Illinois, Missouri, India, and Indiana. But, although this is the surface map for the event that caused the outbreak, but we're going to dive deep into the meteorology of this outbreak because there's much more to an outbreak than just the tornadoes it produces. Let's dive into the meteorology of May 16th, 2025. Now, one ingredient that you need for every tornado outbreak ever is moisture. So let's go back 3 days before, and you can see that we have a lot of moisture here in the Gulf of Mexico, multiple 70s dew points, and lots of dew points already floating inland. Most of the eastern USA was in the 60s, and this continued to build throughout the next day, and come May 15th, you can see that there's a big low-pressure system off of the Colorado Rockies, which is where they typically form due to winds tightening up once they go over the Rockies. So this low pressure system formed, intensified, and began to drag up more and more moisture, and come May 15th, you had a really healthy photo. As May 15th went on, the low kind of ejected up to the north, and 70s dew points began to infiltrate. And you can see here that there is quite a defined warm sector with a lot of easterly winds, with a lot of southeasterly winds, but although at first glance that would look big for tornadoes, it actually wasn't. Why? Well, you just didn't have much speed shear to deal with it. You had strong speed shear kind of up in Wisconsin, but come here, it's not really co-located with where the best moisture was. Like here was kind of weak, like here was strong, but it was blasting extremely dry air up from this area, so that ended up not doing too much. And the Wisconsin risk was kind of the only one that did because it was shielded from that dry air. And now this is the risk in Wisconsin, although the upper level winds were weaker there, so you didn't have much upper level support. You did have some strong low level shear up in Wisconsin, which you did not have further south where there was stronger upper level shear. So thus you had good lower level profiles in Wisconsin, not much upper level shear, like you can see, only 29.4 0 to 6, 42.2 from 0 to 8. Usually those values will be like 60 to 80 if you want it to be good. But we did have a lot of lower level directional shear and good photographs, and we did end up getting a significant tornado. Now for reference, further south in Illinois, at the apex of that strong jet, we had, as you can see, much better 0 to 6 kilometer shear, 42 knots instead of 24 knots, but at the surface, not much directional shear and not much lower level shear. Only 93 0 to 1 and 135 0 to 3 SRH, and thus the only strong tornado we got that day was this EF2 near the town of Juneau, Wisconsin. Now, as the day went on, the surface low stopped moving to the north, and it began to slowly jog to the east quicker. And it became quicker and quicker, and as you can see, more moisture came ashore. 70s dew points infiltrated kind of the southern Midwest, and then they rapidly advected to the north throughout the day. Now, if you look at the jet, you can see the upper level winds become stronger over this area. They became stronger over that area, and you can see how they just become consistently stronger and stronger and stronger, which is much stronger than they were the day before. That's provide a lot of upper level lift for severe thunderstorms. Storms quickly went up on the 16th, kind of in this area, right near the cold front, so near the apex of the cold front in southern Missouri. And initially, so we also had a storm go up in Arkansas. So you can see our lone storm in Arkansas and a bunch of storms in Missouri. So initially, although the storm in Arkansas looks pretty robust, it ended up doing nothing. Why? This is why. This is the storm in Arkansas. Arkansas is further away from the low. So the shear-induced influence from the low, so the wind shear caused by the low, was less in Arkansas than it was in northern Missouri. Because it was less in Arkansas, you can see the lower level shears here is pretty lackluster. Only 99 0 to 1 and 137 0 to 3. And you can see a critical angle 52 degrees, and also because it was so far south, and the air here getting advected into Arkansas is coming from Texas, which is really, really dry, there was a massive EML near the surface that really kind of shut that storm out but prevented it from doing anything. But let's look at these storms in Missouri. Ooh, much better. You'll see how Missouri is closer to the low. That's why the shear is larger. So the shear is larger. The warm nose's magnitude, it's still there, but it's less. But you can see how it's much cooler at 800 millibars in Missouri compared to in Arkansas. And you just have more shear, so overall, a much better look for severe storms was present in Missouri. Now, as storms matured, you can see the Arkansas storm die off, a left split formed, but this ended up not doing anything. But really, the storms of interest at the time was this one, which ended up doing nothing after getting hit by unfavorable mergers. This one going into St. Louis, and obviously these two in Missouri in that sweet spot. But first, let's take a look from another radar. You can see we have a mature supercell over here, a supercell over here, one near Steelville, and a group of storms near Missouri. Now, initially, the storms kind of here, although they look really, really mature, it was still pretty dry over there. Like you can see, although this is definitely exaggerated, but it still showed it's pretty dry. Lower level shear was still a bit weak, but obviously the dry dust is probably exaggerated here. It was still pretty dry at the surface, so that really kept these storms from doing anything. Although the northern storm did end up producing several tornadoes. But the storm of interest, which is up closest to the warm front, as you can see here, if I can go all the way back here, close to the warm front, that's where the temperatures are the lowest, and that's where the air is the most moist, so that's where the least dry air is, was this one going into St. Louis. And now, you've probably heard of the concept of the nudger, where another storm hits a tornadic supercell from the southwestern flank. Why does the nudger theory work? Well, a mesocyclone and a tornado is essentially a really defined area of rising low pressure. And now, if you have the downdraft of another storm, as the FFD of a supercell is a downdraft, if you put a downdraft right next to an updraft, that will magnify the speed of winds that are going from the downdraft to the updraft, and that will help to strengthen the updraft. And that can lead to enhanced tornado potential. And as you can see here, this storm crashes in here, the hook echo curls here, and then you can see this hook echo swing out here as the storm completely continues to crash in and puts that downdraft next to that updraft. And now you get a hook feature up here at the finish of that merger. And then here you have your debris ball and our tornado. This storm produced the first major tornado of the day. It was a major EF3 that touched down in central St. Louis, moved through Richmond Heights, moved across the park, and did a lot of EF3 damage in this area just northwest of the city center. It was pretty bad, and unfortunately it claimed a few lives as it destroyed several brick homes. And here is a video from a security camera showing the storm. As you can see, the storm was up near the warm front. It's not too surprising that you can't see anything because it was up to the warm front. The temperature and dew point spread was probably really moist. So the LCL heights are pretty low, probably a lot of moisture. You can't really see much going on. And also this radar shot should be enough to tell you that there's probably, like you'd see that hook echo is really precipitation filled. There's probably a lot of precipitation in there. You're not going to see it much. And that's what happened. Now, let's go back to our storms in Missouri. We have our southern storm here, which is battling that dry air as we showed earlier. We have a bunch of new storms here that are not doing anything because they're getting shunted by the stable air caused by the wake of the storm. But then the storm to the north is actually the one that was tornadic. Why was the storm to the north the one producing tornadoes in this scenario? It produced two. Produced an EF1 and even an EF2 during the time frame where this supercell ended up producing nothing. Well, remember earlier how that sounding showed a lot of dry air at the surface? Because this supercell was located so close to the major one south of it, the southern storms, actually FFD, probably cooled the temperature that the northern storm was intaking by a bit, thus decreasing the temperature and dew point spread and maybe giving the northern storm just small enough of a temperature dew point spread to end up producing these two tornadoes. And as you can see here, this is an estimated sounding area at the time. It's pretty dry at the surface. There's kind of a lot of dry air, but having the flank of the southern storm and the inflow of the northern storm probably cooled down the temperature and lessened the dry air that the northern storm was intaking. Even though the southern storm is much smaller and the northern storm was much weaker. You can see 50,000 foot tops of the southern storm and only 40,000 foot tops of the northern storm. And as you can see here, you can see the southern storm and the northern storm. But after it produced that second tornado, the northern storm kind of got cut off. It went further away from the southern storm's influence, so it lost access to that enhanced dew point spread, and other storms went around it and kind of began to overtake it. You can see one go up here near Marble Hill. The northern storm loses its influence. The southern storms remains mostly intact, but does nothing until another application of the nudger theory, in my opinion, comes into play. A rogue thunderstorm went up just behind the supercell at about 21 UTC, just as it was about to approach the tri-state border near Cairo, Illinois, the tri-state border of Missouri, Illinois, and Kentucky. Here's another application of the nudger theory. As the downdraft of the storm came right near the updraft caused by the mesocyclone, it probably did enhance the downdraft to updraft wind enhancement, it probably caused a downdraft to updraft localized wind enhancement, as having a big downdraft next to an updraft will magnify the speed of winds going into that updraft. And it enabled this storm to produce a tornado. It was an EF3, and it did a lot of damage, and unfortunately, if I remember correctly, it claimed a life. But as soon, that storm quickly cycled, and then for the next hour, that storm got no other help. So notice how this storm did absolutely nothing. No merger, no merger, no merger. And then when it got a merger from behind, it produced a tornado. Then it produced that tornado. Tornado dissipated, lost that merger. And then for the next hour, it did pretty much nothing. Now, I'm sure you've noticed that as the warm front began to lift began to lift to the north, and here's the estimated environment at the time of this supercell, which showing how that merger probably helped overcame it. It's probably, there's way too much dry air. It obviously wasn't this dry, but you can see kind of that warm nose peeking through. As the system continued to eject, the warm front just shot north, and then all of a sudden you can see the warm front rise all the way into southern Illinois and into Indiana. And at 22 UTC, all of a sudden you're looking, wait, Indiana's in play. We have the tornadic supercell over here, but there is much more usable moisture to the north now. At 20 UTC, as expected, convection from the same so this is from the same storm complex that had produced the EF3 in St. Louis about 2 hours before that. And it continued, and as the warm front continued to lift, and as the atmosphere here continued to destabilize, more and more convection went up. As the next hour passed, this storm, which you can see near Louisville, Illinois, became mature. Passing near the town of Robinson, Illinois, the same town hit by the EF3, near missed by the EF3 on March 31st, 2023, you can see that storm become dominant. And all of a sudden, although it probably exaggerates what was at the surface, you can see it's right along the warm front, directional shear is better, solid low-level shear, really, really, really good up mid to deep layer shear, 75.3 knots from 0 to 8 kilometers is perfect. That means you will have a lot of updraft venting, and you will have really efficient supercells. As that storm continued to induce the environment, and as the warm front continued to lift, the environment ahead of the storm continued to destabilize. That storm suddenly became much stronger, and then it began to take on a tornadic look. And then you can see the change from here. The lower level photograph continued to increase, really good, and the amount of dry air at the surface modeled began to decrease as well. And eventually, we ended up getting our first tornado with this storm right along the warm front. Directional shears also increased as well as the storm approached the warm front. And we got a major tornado northeast of Linton, Indiana at about 2250 UTC. This one was an EF2. Unfortunately, it killed people in a mobile home, but it mostly tracked from northwest of Linton, just tracked north of Linton, and then ended north of Elliston, Indiana. But that was just the first of 3 major supercells that this tornado would produce. Soon, the tornado went into the Bloomington area, and with help from the warm front, notice how it kind of doesn't have another feature here. It produced another strong tornado that went south of Bloomington. This one did EF2 damage and passed through the Clear Creek subdivision, which is just south of Bloomington and the University of Indiana. And then the supercell recycled one more time and produced the strongest tornado that it did. It went south of Nashville, Indiana, and thankfully went into a forested area and produced a major tornado that it was rated EF2, but I'm positive that it was probably EF3 or stronger. Look at the debris ball, but do you see this radar spike south of the debris ball? Following the beam of the radar beam's going this way. You can see that spike. That is a TBSS. That means that probably the debris in the debris ball was so strong that it was actually kind of messing up the radar beam a bit. This is signatures commonly associated with hail, but you can see it sometimes in really, really major tornadoes, like the Mayfield tornado from 2021 also had this. And then here's the scar that tornado left behind. Thankfully, it remained almost entirely in a forested area, did a lot of damage, and then as soon as it entered more populated areas, it weakened and then thankfully lifted right before it hit this subdivision. The storm quickly fell apart, but that storm, which is this one here, quickly fell apart as after producing that last tornado. So this is the time at that storm produced the Linton tornado, and you'll notice a few things. Our storm here, which produced the strong tornado over here, the southern storm, by this time the northern storm that was following it in Missouri had dissipated by this point, is now moved into Kentucky and is crossing the path of the 2021 Mayfield tornado. Here in southern Illinois, we've had another storm go up, and then here in Indiana, we have our tornadic storm. This storm along the line kind of didn't do anything. It was kind of going into stable air. into the stable wake from this supercell. So this didn't do too much, and this is just a left split. Never became right, never rooted onto the right moving motion and didn't end up doing too much. But then, as you can see, let's look at the lower level jet. As time progressed, the lower level jet got stronger and stronger, and you saw how shear increased to this supercell between 21 to 23 UTC. Let's see it in action. You can see between 20Z and 22Z, see how the lower level shear became significantly stronger, especially along the warm front here, and even just across this area in general, you can see it become much stronger. And then from 22 to 23, it becomes much stronger further south. So that means that the environment further south for these storms is becoming much more favorable for tornadoes, for this one and this one. So let's go. Now in southern Illinois, you see this supercell right here? Pretty robust supercell. Let's take a sounding just south of it. I wonder what that environment looks like as the lower level jet continued to improve, and my goodness. 341, 0 to 1, 412, 0 to 3 of SRH, those values are really, really high. Sure, there's a little bit of a dry inversion here, but I call BS on that. It's just rat bias, probably wasn't the case. You can see good lapse rates here. And honestly, this is just as good as a tornado environment as you're going to get. So given that that environment was just south of this supercell, what do you think that supercell was doing? I wonder. And in the meantime, let's check in on our lone supercell. The supercell that only produced a strong tornado when it had help from a merger using the nudger theory. It actually did produce one more tornado, but if you'll see, it latched onto a boundary and probably benefited from some vorticity there. So that storm produced a tornado, and as soon as it fell off that boundary, that storm went back to just vibing, not producing tornadoes. But then we took this impressive sounding over here was taken just south of this supercell. Initially kind of has a long flank there, but as time passes, that supercell becomes stronger, and as more precipitation closes in on the back of it, you can see precipitation here hit, gives it kind of a nudge, and that supercell surged really, really quickly. You can see storms go up around it, and that supercell began to surge. And given how strong the environment is here, I mean, you could only expect what this supercell did. And then from there to there, a major debris ball appeared. This storm ended up producing an EF4 tornado that passed south of the town of Marion, Illinois. Fortunately, nobody was killed. Multiple extremely impressive videos were taken of this violent stovepipe tornado, and it did do EF4 damage when it leveled a home, and it was actually rated high-end EF4. Whether it deserved the high-end EF4 rating or not, I'm not exactly sure. A lot of people that I know who are more knowledgeable about me when it comes to damage ratings disagree with the official rating. And then as that storm continued to move to the north after the Marion tornado dissipated, so this is when that tornado dissipated, it tried to produce again, and you can see here it flanks again, but then unfavorable mergers, you can see a storm went up just in the inflow region. Usually, although mergers from behind are good, mergers from storms that go up in the inflow region are not good. Why? Because they provide stable air. You do not want to have stable air going into your inflow, into your tornado, or else not much good, tornadic-wise, will happen. So that, you can see that fell apart after that became stable, fell apart right here. The storm didn't look organized, but then notice how the inflow was now clear. And as soon as that inflow is now, with that inflow cleared, with that stable storm removed from the inflow, and as another much larger storm with a much larger downdraft crashed into the back of that supercell, it surged. It surged really quickly. This storm produced its second and what would turn out to be final major tornado south of the town of Morganfield, Illinois. It was an EF3, and this is the scar left behind. So this is Morganfield, and it went south, did a lot of tree damage, it did EF3 damage, but thankfully didn't last too long. And this is the damage intensity path. Orange triangles represent EF3 damage, yellow EF2, green EF1, and blue EF0. This circle represents wind damage. Thankfully, it missed the town of Morganfield. Now, this is at that time. Another big supercell had gone up over here, and by this time, the Indiana convection had completely dissipated. Another supercell went over here, but it kept getting bombarded with bad mergers. Storms kept going up on the inflow, and it did nothing. After that, you'll see what happens to the Morganfield after that. Morganfield supercell after that. And then our supercell here, the southern storm in Missouri that formed all the way here, produced the major tornado here, then latched onto the boundary here, produced a tornado, and then had another merger here just north of the AKHPX radar and produced a tornado there. It's still vibing, but it's really not doing too much. It's relying on kind of nudger processes and just boundary processes to produce tornadoes. But let's see what happens to the lower level jet. The lower level jet kept on increasing and increasing. It just got stronger and stronger. You see how much stronger it gets? It just got so much stronger. And the lower level shear just kept on going up and up. And near the town of London, Kentucky, as the temperature cooled and the moisture went up, dew point slightly increased, and you can see the dew point temperature spread decrease as time passes. And look at the environment. Let's take a sounding here in southern Kentucky, just near this storm. Near this storm, as convection behind it slowly closes in on it, the shear ahead of this original storm, our original storm that went up in southern Missouri, is increasing significantly. Look at that lower level shear, 293, 356, really good. But now you can see how the deep layer shear is increasing as well. Lower level shear is increasing, bigger photographs, but 94.1 knots of 0 to 8 kilometer shear. My goodness, that updraft became extremely impressive. So this was the Illinois supercell that produced the EF4 and the Morganfield EF3. You'll see it fall apart as more convection crashes into it. Stable storms keep going up in the inflow, and eventually that storm completely falls apart and it gets embedded into a line feature. So that's what happened to that storm. But let's look at this storm. This storm is an environment with increasing moisture, decreasing temperature, which means that the temperature to dew point spread is less, which is better for tornadoes, and the lower level shear is only increasing. So this storm kind of vibed, but as more and more storms kept on closing in on it, and as storms kept on forming near to it, and it kind of nudged it a little bit just to help, this storm ended up doing exactly what you would expect it to. As you can see here, lower level shear is increasing, deep layer shear is increasing, moisture is becoming more favorable for storms, so there's more potential for nudging. And as it moved near the town of Somerset, it turns out that the atmosphere had saved its worst surprise for last. 9 hours after the storm first went up in southern Missouri, it dropped its final tornado. The tornado first touched down south of the town of Cade Store, Kentucky, and this is the tornado genesis. You can see here, pay attention here, reflectivity, and this is correlation coefficient. Look at this again. You see here, nothing, but boom. See that blue? See that orange area? That's the debris ball appearing in here. Velocity. See that really small area of strong winds going towards the radar green, going away from the radar red? That's our tornado. And you can see the debris ball just continue to improve in intensity. The tornado first touched down south of the town of Cane Store, did a lot of damage, but thankfully, as it moved towards the town of Somerset, it weakened and only did EF2 damage as it went through Somerset. The tornado by itself wasn't very large. It was often seen as a stovepipe in the available videos of it. But then, as it moved into forested areas past Somerset, this is the path through Somerset. You can see it weakened a lot as it went into the town. So you can see here, and then it went through southern Somerset, but it was much weaker than it was here. Here, the path is much more defined. That changed. You see this? As the storm went into the forest, the tornado became stronger and stronger, and it became larger and larger, and it began to do absolutely ridiculously intense damage. Look at the forest go. You can see how the tornado just got stronger and stronger and wider, and it began to produce EF3 to EF4 damage, and there was actually some EF4 damage indicators observed in the forest. And then that supercell kept it up. Although the supercell began to weaken and the tornado thankfully began to downsize as it approached the town of London, Kentucky, that wasn't to last. Sometimes, if you have a large but relatively broad tornado, and that tornado suddenly shrinks into a smaller vortex, laws of physics say that the speed of that vortex, assuming that energy is the same or remains mostly the same but decreases at much lesser rate to which the vortex shrunk, the speed must increase. And that is exactly what happened when it went into London. Here, you can see the tornado, large, strong, thankfully begins to weaken here. But then as that vortex shrunk, the energy level didn't decrease that much. And all of a sudden, here, all that energy got focused into a new, much smaller, much more defined vortex. So think of it here. It was large and kind of broad, but then it took take that same energy that's pumping this large and broad vortex and pump it into a much smaller vortex. You'll get a much more defined and devastating vortex. And it ripped into southern London, and it did absolutely catastrophic damage to this subdivision, the Sunshine Hill subdivision. It did multiple areas of EF4 damage, completely slabbed multiple homes, and it heartbreakingly resulted in the deaths of 19 people. It was just incredibly unlucky that this tornado, out of all of the places in which it could reformed on in its life, here you can see its lifespan. This is where it first touched down. It weakened the first time it went through a populated area, then became really strong, and then weakened again. But the last time it reformed with major intensity, it happened to reform right over a subdivision. And this is the outbreak when it finally finished. after the London tornado dissipated, you can see here more storms are catching up to that London supercell. This supercell is not going to do anything because it's being shunned by the stable air from the London supercell. And all you can see mergers begin to go up in the inflow region of that London supercell, putting stable air into the tornadic circulation that will eventually kill it. When all was said and done, I mean, yeah, you can see our supercell pass here. So this is the EF4 that hit Marion. And then it ended up producing 2 more weak tornadoes. I actually did not know that. But notice how those tornadoes never became significant because of those emergers into the inflow. But then it produced that big EF3 near Morganfield before it got overtook. This is our long track supercell. Produced that EF3 tornado here for the merger. Nothing. Produced that EF1 tornado when it had that merger. No, when it had the boundary interaction. Nothing. Had another merger. Produced the CF2. Did nothing. I think that was from another storm. And then it kept on going straight. And then as conditions became more favorable, the LJ ramped up. And everything just became much stronger. It produced that final catastrophic EF4 tornado. Sometimes nature saves its worst for last. And as the system kept on moving and as the lower level shear kept on going up, the temperature and moisture spread kept going down. Nature saved its worst for last. Thank you guys for watching, and I hope you really enjoyed this video.